When we think about communication, we usually think about people, right? Or maybe our pets. But what if we could go smaller, way smaller? What if we could actually talk to the microscopic world? I mean, literally have a conversation with bacteria to help us solve one of the biggest problems on the planet, water pollution. Well, today we're diving into an incredible story where a classic math equation becomes the secret language to do exactly that.
It sounds a little like science fiction, doesn't it? But seriously, what if? This very question is at the heart of our story today. It's all about a young environmental engineering student who, while staring down a puzzle in his lab, accidentally figures out a way to not just watch bacteria, but to actually listen to what they have to say.
So let's set the scene. Meet Pawkin. He's a student, he's in his university lab, and he's surrounded by all the humming and bubbling of a bioreactor. His experiment is supposed to be simple. He gives bacteria and wastewater more food, in this case sugar, and then he just measures how fast they grow. He's expecting a nice, simple, predictable result, but what he gets is a total mystery. And this is where things get weird. On the left, you see what Pawkin expected, a straight line. More food equals more growth. Makes total sense, right? Simple. But on the right, that's reality. That's the data he actually got. It's this strange curve. See, the growth speeds up for a little while, but then it just flattens out. It hits a plateau. No matter how much more food he dumps in, the bacteria just don't grow any faster. It's like they have a speed limit. So, completely puzzled, Pawkin takes his weird graph to his advisor, and his advisor pulls out this, the monod equation. It's this old formula from way back in 1942, but it's like a secret code that perfectly describes the curve Pawkin was seeing. Let's break it down real quick. Mu is the growth rate. That's what we want to know. S is the amount of food, but the magic is in the other two parts. Mu max is the bacteria's absolute top speed, and Ks is the amount of food they need to hit just half of that top speed. It's basically the complete recipe for their behavior. So Pawkin rushes back to his computer, plugs his own numbers into this old equation, and it's a perfect match. I mean, perfect. The curve the math predicted was almost identical to the curve his actual living bacteria had created. It was this beautiful moment where a clean, elegant formula was able to perfectly describe a messy, complex living system. For a minute there, in the quiet, controlled world of the lab, he thought he had the whole answer. But you know how these things go. That perfect fit in the lab, it was really just the beginning of the story. Because late one night, as Pawkin is staring at his data, he gets this nagging feeling that something is still missing. The equation worked, sure, but it didn't feel like the whole story. It was almost like the bacteria themselves were trying to tell him something else. And then, in a classic late night in the lab flash of insight, it hits him. It's as if he can almost hear the bacteria whispering to him. They're saying, hey, not all the food we eat goes into making more of us. A huge chunk of that energy is just for basic survival, repairing their cells, moving around, just staying alive. It's what scientists call endogenous decay. It's their cost of living. So what does this mean? It means the model had to evolve. Pawkin realized he needed to add a new piece to his puzzle. He adds this term KD, the decay coefficient. This is basically just a number that accounts for all that energy the bacteria are wasting on just living instead of on growing. It makes the math a little more complex, sure, but it also makes it a heck of a lot closer to the truth. Okay, so Pawkin's feeling pretty good now. He's got his new, more sophisticated model, and he gets the chance of a lifetime to test it out at a full-scale, real-world wastewater treatment plant. This is it, the ultimate test. Is his neat and tidy equation gonna survive in the messy, chaotic, completely unpredictable real world? And the result? Oh, it was a disaster, a complete and utter failure. His model, the one that worked so beautifully in the lab, predicted the factory's water should come out with less than 30 milligrams per liter of pollutants. The actual number? 90. It wasn't just off by a little bit, it was off by 300%. The formula had completely and totally failed. So, what on earth happened? Well, the real world happened. Turns out a factory is nothing like a lab. You get these sudden toxic shocks, random chemical spills that just stun the bacteria. The water temperature is all over the place, and crucially, the oxygen levels in the tank would sometimes just plummet, basically suffocating the very bacteria that need it to breathe and do their job. His simple model just couldn't handle any of this chaos. But this failure is actually where the big breakthrough happens. Pawkin realizes the monod equation wasn't wrong, it was just incomplete. It was a fantastic foundation, but it needed more layers. So he started adding new terms to the equation, new pieces of math that could account for those real-world problems, like changing oxygen levels and wild temperature swings. He was making the equation tougher, smarter, and more adaptable.
And this is where the story goes from interesting to truly groundbreaking. Packen has this incredible idea. What if the equation didn't have to be a static set of rules? What if it could actually learn and adapt all on its own in real time? He decides to build something he calls a dynamic monode model by fusing that old school biology formula with the power of modern artificial intelligence.
So how does this AI brain actually work? Well, you can think of it like a four-step dance that's happening every second of every day. First, it senses. Real-time sensors in the tank are its eyes and ears, constantly measuring everything. Second, it learns. A machine learning algorithm is just churning through all that data, looking for patterns. Third, it predicts. Based on those patterns, it tries to guess what's going to happen next. And finally, and this is the absolute magic, it adapts. It literally adjusts the variables in the monode equation on the fly, rewriting its own math to perfectly match reality. So he builds this system, this AI, and he names it Monoda. Then one night, while he's monitoring it, something absolutely incredible happens. A message appears on his screen. A message he didn't program. The system itself communicates with him. It tells him it has stabilized the system and reached the best possible state. This was the moment the equation didn't just calculate life. It truly came alive.
And the results in the real world, they were just stunning. With Monoda in charge, the factory's treatment efficiency jumped to an amazing 92%. But not only that, because it was so smart about using the air blowers, which are the biggest energy hogs in a plant, it also cut energy use by a whopping 18%. It was a huge, undeniable success.
Now, the story doesn't end at just one factory. That would be impressive enough. But Packen's living equation, Monoda, had proven its point. Its potential was so much bigger. This wasn't just a tool for one factory. It was a whole new way of managing a living ecosystem with the potential to help an entire city. And check this out. This chart shows something called the Sludge Volume Index, or SVI. Think of it like a report card for how healthy the whole bacterial community is. Before Monoda, the SVI was way up at 180. That's a feeling great. It means the bacteria were stressed and unhealthy. After Monoda took over, it dropped all the way to 95. That's an A+, a sign of a thriving, happy ecosystem. The system wasn't just cleaning water, it was actually making the bacteria healthier. And Monoda just kept learning, kept evolving. It started to optimize itself with no human help needed. It learned how to handle those toxic shocks that used to be a total disaster. And then it did something that blew everyone away. It analyzed all the city's data and proposed its own plan to connect to the entire municipal network to make the whole system more efficient and sustainable. It had gone from being a tool to being a partner. And so we end on this quote, which just captures the whole journey perfectly. It all started with Jacques Monod, who discovered this fundamental law of microbial life way back in 1942. But it took Pelikan, a curious student who was willing to listen, to take that mathematical law and give it a soul. It's an amazing story, and it really makes you wonder, doesn't it? What other secret languages are out there, all around us, just waiting for us to learn how to listen?